what is the beat frequency? If I played a 440 hertz note and a 439.5 hertz note.
What is the what?
The beat frequency. If I play these two frequencies at the same time.
Isn't it just a half or 0.5?
It's a half a hertz, and therefore, what is the period?
Same.
Would it just be 1/2? Or half? Not 1/2.
It's the flip, reciprocal.
2/1.
What's the reciprocal of 1/2?
1 over.
Okay, 1 over a half, which is?
2/1.
Yes. So we'd expect it to get quiet every 2 seconds. 1001, 1002, 1001, 1002. So the closer they are to each other, the more drawn out the period is, and at some point it's close enough. So if any of you have ever seen a piano tuner, this is basically what they would do, is they knew what the frequency would be for the string. They would play the tuning fork, play the string, and then they would listen for how well they matched. What was the beat frequency? You want a high beat, you want a low beat frequency or a high period. And so they would tune it, so then they would adjust the tension in the string in order to adjust in essence, the harmonic, which would adjust the speed of the wave, which would adjust the harmonic.
So T stands for period in this case?
Yes, capital T for period.
Okay. And to get the 2, you did 1 divided by 0.5?
Yes.
Okay.
So 1 over the frequency is the period, and so in this case, the frequency was 0.5. So 1 over 0.5 is 2.
Okay.
Another way of looking at that, 0.5 is the same as 1/2, and the reciprocal is just taking any fraction and flipping it over. So we'll do the tube, we'll play the frequency that we predicted, the 417.26, and see if we can hear the beat frequency. Not necessarily going to hear it, but let's just see if we can. If it's dead on, which of course we would expect, 417.26. Just so hear this thing. It's a little bit of a trill there. And without that, I'm definitely hearing a trill when the other sound is playing, which means we're hitting a beat frequency, which means we're somewhat close. If you can notice the difference, maybe we're 10 hertz off. That could be good. Let's see, if we're 10 off, what would that sound like? 427.26. That's 10 hertz off. Hertz off. I think we were somewhere between there, but I don't know. Let's predict the next harmonic. The third harmonic. I know that the wavelength is going to be 2/3 of that length. Let's see that. So the wavelength is 2/3 L for the third harmonic. And we have a wavelength of 0.882 meters. No, sorry, doing that wrong. L is 0.822. So this is equal to 2/3 times 0.822 meters. 548.
Yeah.
And so the frequency I would expect to hear is going to be the speed of the wave divided by the wavelength, which is 343 meters per second, divided by 0.548 meters.
I think 625.
625.
Yeah.
625.
Oh, yeah, sorry, 0.91.
Okay. Units.
Those are meters, or seconds? No, sorry. Hold on.
Anyone?
Hertz.
Hertz.
I knew that. Hertz.
Again, 1 over seconds. All right, so let's get the sound going. We'll play the tube and we'll see how close we get. So prediction was 625.91. Kill that. Second. Yep, that's third. Yeah. Dead on, perfect. All right, anyway, 2 free ends. Now, as we're dealing with sound here, there's certain frequencies people can hear and cannot hear. Now, the older you get, the less frequency, the range narrows what you can actually hear. And I also have tinnitus, so there's, in terms of listening, somewhere in the 8,000 to 12,000 hertz range, I don't hear that, because that's basically the ringing in my ears. Then I hear sound again at some point, and then it goes away just because of, not tinnitus, but age. So what I'm curious here is, I'm gonna play it, it's gonna start out at a low frequency. As it increases, when you can no longer hear it, just raise your hand. A number of years ago, before class began, I was making sure this was set up, and I had it at some frequency and I forgot to turn it off, but I couldn't hear it because it was above my hearing range. And at some point early on in the class, someone said, "Is anyone else hearing a strange sound?" Yes, they could, I could not. Hearing test, there we go. $5,000 hertz. 6,000. 7,000.
8,000.
Yeah. All right, I'm out.
9,000.
10,000.
11.
I'm back.
12. 13. I'm gone.
All right. I'm on it also. Rest of you can hear it still? No,
Nope,
okay.
it went away.
We're up to 16,000 hertz. Hunter, you're saying that you,
No, I don't hear it.
you don't hear it?
No.
Good. That's 20,000 hertz right there.
I don't know. Oh, no.
However, Latoya, the advantage is, you bring up online tone generator, you put it at some frequency that you can't hear, but your kids can, and watch the fun. All right. Now, when I was swinging the tube, I was swinging it vertically on purpose. If I'm swinging it like this, the question is, do you hear an extra trill in it when I'm swinging it horizontally versus vertically? So here's vertically again, horizontally.
When you do it horizontally, you can like hear it dip.
Anyone, do you know why?
What?
It like nodes and antinodes.
Okay.
It's not a node antinode thing actually in this case, for that extra dip.
Would it be because of fixed ends and free ends?
No, fixed and free ends and the nodes antinodes, that gets us the frequency that the tube is producing. But there is a difference in this particular case versus this case. In this case, the end of the tube is going towards you and then away from you. Whereas in this one, it's pretty much the same. That's the Doppler effect. We're now about to see some incredibly award-winning drawings. Or maybe, you know what, I'm just gonna go to the video because their drawings are a lot better than mine. And because of this video that I'm about to show, there's going to be some warning that's going to pop up on YouTube that I will see, saying that I'm using copyrighted materials. I did have a video banned in 4 countries for showing a video from the 50s. Come on, fan. So imagine that a sound's being produced, and as the sound waves, basically they're pressure waves, you get these high pressure waves that are being sent outwards. If something is coming towards you, let's say that you're singing a perfect note, perfectly pure note, as somebody comes towards you, they're going to be hitting those pressure waves more frequently as they come towards you. They will register that as a higher pitch. Now, I don't think I've done it yet today, but at some point I probably would. I use pitch and frequency interchangeably. If you've had music theory, I suspect that that's a big no-no.
Well, no, I've never taken music theory.
Oh, okay, all right. Pitch and frequency, I think there's officially a difference. I don't care. So if someone's going away from you, they're going to hit those pressure points. It's the pressure, the high pressure points. Not the word I'm looking for. The high pressure areas less frequently because they're going in the same direction, so it's moving away as the person's running or whatever's moving, and so you hit it less frequently.
I know. What is this commercial? I can't tell what's
Sound probably.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples in a pond. Those are all waves.
All right, so the black lines here would represent high pressure, and in between would be the low pressure. So this would be compression and rarefaction. So the sound is produced, you get this high pressure ridge moving outwards.
and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it,
So as it's moving in the direction of one to the side, the next wave is emitted closer to the previous one, and so smaller wavelength, higher frequency, and over here, a bigger wavelength and lower frequency.
they're spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of the road. That's you, and the car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is.
And these would be electromagnetic waves, which we talked about earlier. These are not mechanical waves like sound is.
Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this magic difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
I don't do an hour cardio. I have never done an hour cardio in the past 5 years.
Now there's a formula that I'm not going to subject you to, but as with anything with physics, there's always math that can go with it. So now, let's take our idea of Doppler shift and extend it. So I have an object here emitting a wave. So that wave will then, you get that high pressure ridge, and then another high pressure ridge, another high pressure ridge. Assume that all these circles are concentric, that they all have the same center. If you start moving after the first one, so if you create the first wave and that wave is start going out from where you created it, but you move closer to it, this is what was shown in the video, you do the second wave from there, and so as that first wave centered around that point, it's bigger, the second wave centered around that point, they're closer together with the higher frequency. And so if I had drawn it out, it would have been something like that. But let's take it to that next step. Suppose you're traveling faster than the sound wave is traveling. So the first wave gets created from wherever you were at that moment. And then you're you're now here, because you're on the other side of the sound wave. If you create a sound wave at that point, well, you have the first wave has gotten bigger. The second wave centered around a different point. and now you create a third wave. And so what you would end up doing is you keep creating sound waves. Now what is happening, right there. Remember, the line represents high pressure.
Is that what's happening right there?
Yeah, what is happening right there?
The pressure is higher? The pressure is higher?
Yep.
The pitch is higher?
Not the pitch. Pressure is higher. What kind of interference is this?
Would the volume be higher?
Oh, yeah, definitely.
Starts with a C.
Sorry?
Does it start with a C?
It does.
Correctional or
Constructive.
constructive?
We have several of these frequencies that are overlapping at this point, several of these high pressures overlapping. So if I have something that has this much pressure on top of something that has the same amount of pressure, together they're twice as big. If I have a third one there, it's 3 times as big. The more of these high pressure areas on top of each other, start getting much more pressure. Wow. We'll try English. As the pressures build up, you start getting orders of magnitude more and more pressure, potentially. And this type behavior has a name. It's known as a sonic boom.
For real? That's good.
Extra credit for everyone.
So all you need is for something to travel faster than the speed of sound to create a sonic boom.